So very good evening to all of you. So I welcome to this first live session for this course, Computational Fluid Dynamics for Incompressible Fluid Flows. I think already 2 weeks are over. So you are actually learned some basics of these application of CFD as well as the discretization techniques using finite difference method. So if you have some questions here, we'll discuss today. And we received a few questions in the MS form as well, and that I am going to discuss few of them. And if you have any other questions, you please post it here or in the YouTube link, or here also we can discuss. I think let me first discuss with Mr. Suman. So can you please tell me, means you are a research scholar or you are a industry person? You please unmute yourself and please tell. You please unmute yourself.
Yes. Hello, sir. Good afternoon. Am I audible?
Yes, yes.
Yes, sir. Sir, actually, I have completed my master's degree. Actually, I am a mechanical engineer by graduation, and then I have completed my master's degree in nuclear engineering from Jadavpur University in Kolkata.
Okay.
And now I am looking forward to apply for a doctoral program.
Okay, so I received few questions here, so I will discuss a few things. Okay, so you please mute yourself, and if discussion required, then that time you please unmute. Okay.
Okay, sir.
Okay, thank you. And if any other students are having any questions, you please post it here. I hope you are able to see the screen. Now I will discuss few questions given by Mr. Suman. So he's asking that what is exactly known as modeling? Can you please explain it with suitable examples? Why do we need to use or create models? Say modeling in CFD, it is something different. Like you have seen that we can use in different perspective this modeling. Say modeling starts from what problem you want to solve, right? Say you have a given problem, whether it is industry or some basic R&D problem. Now modeling means now there are different steps are there. So first you have to make the geometry, then you have to discretize using grid, then you have to choose some suitable what I'd say scheme for discretizing it, and if some multi-physics are involved, then you need to use specific models for that. So as a whole, you can tell that it is a modeling, and using numerical technique, generally we solve this kind of problem. Now, when you are talking about your one question, next question, that flow through the porous region is modeled using Darcy model. So now you can see here one specific physics is involved, that is that flow through a porous medium. Now, porous medium, how to solve a problem? Okay, so one thing is that obviously you can have a porous media and you can have the grid only in the fluid domain, and solid domain you can separately have boundary conditions. But it is very difficult because you can see to have a porous media separately to model it using the solid part and fluid part, it is very difficult. So for that, actually there are some models available, which is here it is known as Darcy model, so that it uses that it is homogeneous porous media, so that the porosity whatever you are considering, that is uniform everywhere, and you have the only single domain where you solve it without separating the solid domain and fluid domain, but you use porosity and use the Darcy model, so that in a simple way you can solve this problem. So that is the modeling thing. So obviously here you can see in other specific, say multi-physics, if you have a say multi-phase flow, or if you then you have to track the interface, and that time tracking interface, there are different methods available. So one of the well-known method is volume of fluid method, okay, VOA. So here you need to solve one advection equation, okay, and other method is that level set, or combinedly level set plus volume of fluid you can use. So now this another technique, now you have to use it to differentiate the solid domain, the fluid domain and the gaseous domain, right? So so that time volume of fluid method you have to use. Say solving Navier-Stokes equations, okay. Now there are different methods are there, like simple algorithm, simpler algorithm. So you can see that you have to choose a suitable scheme for solving that, and based on your experience, expertise, and knowledge, which scheme you will use for the given problem, that you have to judge. So there is no specific way that you can use this model or that model, not like that. So all model will give results, but some extent there will be some maybe some difference, okay. But it depends on your understanding about the problem and which way you want the accuracy, and whether it is industrial problem or your research problem. Based on that, how much accuracy you want, based on that you need to choose the model. Like say if you want to have a very you have seen that spatial discretization, there is first order, second order, third order schemes we have discussed, right? Convective scheme, how you to generally diffusion scheme we use in general second order, but convective scheme generally we use first order, second order, or third order, like quick scheme. But those things you will discuss in later classes. But say now you have to choose that how much accuracy you want for that problem. So accordingly you will choose it. Similarly, say if it is a time dependent problem, then what is the accuracy you want in time direction? First order mostly we go, that is Euler discretization. If not, then we go second order. So there are different methods are there. So that way you have to choose. So it depends on your problem, understanding of your problem, and what accuracy you want. Based on that, you need to choose. So Suman, if you have any doubts on this, you can please unmute and tell. Suman.
No, sir. It's okay. I understand, sir.
Okay. Then I will go to the next one. So,
sir, just one thing. Just one thing. Can you please repeat that definition on modeling, sir? That first question. Can you please repeat it again?
No. Say modeling. It is used in a broader sense. Okay. So modeling means, say you are given a problem to solve numerically. Okay. So there are several steps involved. So which way you model, say starting from creating a domain, then generating the grid, then you need to choose several physics of the problem. So that is called again model. That is different model. Okay. So like Darcy model or some other models are there in different physics. So that how you are going to choose. So as a whole, you can say that it is a modeling part.
Okay.
Okay,
sir.
Next, your question is that
I think there is no fixed method for approaching for a model. It can be anything.
Pardon?
That there is no fixed way of approaching for a model, for making a model. It can be.
No. Say there are steps involved, right? So first you have to create a grid, geometry for your given problem where you want to apply the boundary conditions in different places. You might have complicated geometry. Then you generate the grid. So if it is a simple geometry, very structured grid, you can generate. But if it is a complicated geometry, then you can use different zones, subdivide into zones. Then you can create the grid, and then you have to choose that which discretization method you will use for solving the problem. So before that, you have to choose the governing equations, right? Which governing equations you need to solve for the given problem. Okay. Say if it is only diffusion problem, you will solve only the diffusion equation. But if it is a fluid flow problem involved with other multiphysics, then you need to add all those things, right? So that way you have to choose. Then now say when you are solving a Navier-Stokes equation, so there are MAC algorithm in finite difference method, simple algorithm in finite volume method, or simpler, simplex, piezo, different many schemes are there. So you have to, based on your judgment and what scheme you want to use, that you have to choose. Okay, after having the knowledge of basic CFD. Okay.
Okay, sir. Okay, sir. Okay, sir.
And next is what is meant by domain independence. Say now domain independence means say you have some problem. So let us say you are solving one flow over a so you are solving a flow over a cylinder, let us say two-dimensional. Okay. So now it is a flow over a cylinder. Okay. Now you have to have some computational domain to solve this problem. So whether you will use this domain or you need to increase it further. Okay, so how will choose it? Okay, so you can see that if you are giving some boundary here for your computational domain, then obviously what boundary condition you are applying in these boundaries, as well as at inlet, there will be some velocity inlet here. So now it doesn't have any effect on the solutions because you are solving a flow over a cylinder problem in an unconfined manner. So it is unconfined. So obviously there will be some influence of the boundary conditions here, what you are imposing. So if it is very close to the cylinder, obviously it will have some effect. But if you can have it is far away, then obviously there will be less effect of these boundaries on this problem. So now you have to see that the domain, whatever you are choosing, whether this one, or a greater one, so that the boundary doesn't have any effect on the solutions. Okay, so that is known as domain of domain independent state. So that means you have, let us say, let us say you are plotting CD on this cylinder. So CD will vary, or average CD you are calculating. So if you see that it doesn't have any effect on CD change if you are changing the domain. Okay, so that is the domain of independence. Okay, and next question you have asked smooth solution in CFD, but what does it mean by smooth solution? I also do not know what you are what do you mean by smooth solutions. One way means generally in CFD we do not use this smooth solution, this word, but means what I understand, maybe you are talking about that the solution converges very smoothly. One is that one. There is no means divergence when if it is a iteration with iteration error decreases smoothly, or the solution whatever you are getting that may be smooth. So but generally we do not use this smooth solution. Solution is solution, so it should be accurate solution, right? Whatever you are getting. So what do you mean by smooth? That have you come across with some in CFD this smooth solution?
Yes, sir. I have read somewhere about smooth solution, but I'm not sure what it is. So I thought to ask you.
Okay, generally we generally do not use a solution what you are going to get after say a numerical solution. Okay, it should be
Hello.
Hello. Hello. Hello.
Hello, can you hear me?
Hello, sir.
Yes, you are audible. Sorry, there was a call drop.
Yes,
So
sir. Yes,
what
sir.
I was asking that say source term generally comes like you have a you are solving energy equations. Now you have a uniform heat generation. So how will add it in the governing equation? So it is added as a source term. Okay, because say we have temporal term in the left hand side, which is a time dependent term. Then we have a convective term. Okay.
Yes.
Then the right hand side, generally we have diffusion term. If it is momentum equation, we have pressure term, and rest other terms which are coming from other physics. Okay, that is added as a source term. Like you have energy equation, simple. So energy equation, now if your uniform heat generation is taking place, okay, that time generally we take this uniform heat generation term as a source term in the equation, and as a source term we discretize it. If you have, say, let us say radiation, okay, and from the radiation, after solving a radiation equation which is known as radiative transfer equation, now once intensity is known, from there you will get one term from radiation which is your radiative heat flux, and that you will add as a source term in the energy equation to get into temperature. Similarly, say in the momentum equation, pressure term will be there as it is, we will not call as a source term, but say if you have a electric field or magnetic field, okay, so its effect will come as a source term in the momentum equation, because its effect is there in the fluid flow, right?
Yes,
so that way we just use the source term in the momentum and energy equations. Is it clear?
Okay. Yes, sir.
The next question, obviously, you please, it is a basic mathematics, okay, nabla, divergence, grad, and curl, okay, so that you just go through by any mathematics book, okay. How to learn OpenFOAM? Yes, OpenFOAM is a open source software, and based on the finite volume method. But so obviously means you can learn on your own, or there are some tutorials available in the YouTube. You can go through it, but in this course we are not going through it because this is a basic CFD course. Here just the schemes and methods we will learn here. Okay, and there is a faculty at VNIT Nagpur. He generally floats some course in the summer, okay, for 1 month or 1.5 months. So his name is Professor Tushar Grohil. So he is an expert in the means in this OpenFOAM, and he regularly conducts this short-term course on OpenFOAM. So if you are interested, just for your information, you can attend it. Okay. And is it sufficient to know only C programming in order to use the simulation software properly? Yes, say whatever we are solving, but we'll be solving, you will see that electric equation, then parabolic equation, then Mach algorithm we will use, or simple algorithm. So you can write some program in any language, right? Say Fortran, C, C++, or nowadays people are writing in Python. So just for your understanding, whatever I will be showing here, you write on your own some code which I have shown. Maybe it is not a perfect, very compact code, but you can write a very compact code in 4 or 5 lines. Okay, and then you can get the solution and compare with the available solution. If it is you have an analytical solution, then you compare the result with the analytical solution. So that way it will give you confident that whatever way you are learning in basic CFD course and how it is useful, and when you are writing the code, and there are you know that when you are coding something, there might be some mistake. So means you have to have patience to find fix the bug. So that way means you can get some means happiness after getting the results when you are writing your own code. Okay.
Yes,
and compressible flow solver here anyway it is not scope in this course, but compressible generally we discretize the equation in a different way. Okay, so altogether, because its mathematical behavior is different. Okay, so that's why incompressible fluid flow discretization and means numerical schemes are different than the compressible flow. Like in compressible flow, you may come across with shock where sudden change in the properties will happen. Okay, so whatever we use in the incompressible fluid flow, these schemes will not be able to capture the physics of that problem. So altogether, discretizations are different in compressible fluid flow. Okay, so that's why we are not going to discuss it here. And some questions are there. Say difference between analytical and numerical approach. Obviously, say we have say full Navier-Stokes equations. If it is three-dimensional Navier-Stokes equations, obviously we cannot have a analytical solution for a means three-dimensional or complicated problem. Why? Analytical solution means you can integrate it with the given boundary conditions, then you can get the solution. So that is the analytical solution. Okay, you might if it is a two-dimensional, or if it is a one-dimensional exact solution you can have. If it is a two-dimensional solution, then analytically you can use different method like separation of variables method and but those are limited to some diffusion problem or under certain assumptions. But if you really want to solve a three-dimensional Navier-Stokes equations, you do not have any analytical solution. Okay, so that time the one of the approach obviously is the experiment you can perform, and another is numerically you can solve the governing equations, and we can solve it mathematically. So that is the numerical approach, so using CFD. But analytical solution always you may not have. Only under certain assumptions you can have the analytical solution, and wherever possible, like plane Poiseuille flow between two parallel plates, right? That is essentially will come to one-dimensional problem where velocity is function of only y. If x is the axial direction, there will be no change in the axial direction in a fully developed flow. Or if it is not fully developed, also you can have some analytical solution, but means you need to know the analytical solutions only available under certain assumptions. Okay, and wherever you cannot have the analytical solution, obviously you have to go for numerical approach using CFD, or you can go for experiments. Another question is boundary and domain. Can you please explain how to specify? Say, domain is that say you have a problem. So now you have to tell that how you are going to solve a problem. So for that you have to choose the domain, and in the domain there will be there will be certain what I would say boundary where you need to apply the boundary condition. So let us say this problem what we are discussing. So this problem, if you see that here, say this is the problem is given that you have to solve fluid flow over a cylinder. So now you have to find a domain which is your computational domain, because otherwise where you will solve the governing equations, right? So you have to solve the governing equation in certain regime, right? Inside it is a solid, so you are not going to solve anything, but outside now to capture the fluid flow, you need to have some domain, that is your computational domain. Now you can see if it is in Cartesian coordinate you are solving, then obviously you can see there are 4 boundaries. Okay, so now so in these boundaries you need to apply the boundary conditions. So maybe at inlet it is a inlet boundary, this is your outlet, these may be symmetry, okay, or far field boundary conditions you can apply. So you should have say you are asked to solve a fluid flow problem, unconfined flow over a cylinder. Now you have to choose a computational domain where you will solve the governing equation, maybe Navier-Stokes equations. Okay, so that is your domain, and now you have to apply the boundary condition at certain boundaries. So these are the boundaries. Okay, so say any domain, sorry. So now say you have any domain. Okay, so this is the domain. Now it is the governing equations you will solve. So it is the whole this is your domain and this is your boundary. Okay, so now at the boundary you will apply the boundary conditions. Okay, and governing equations you will solve at the interior points. Okay, I hope that you got it. Okay. No, another question is that is there any thumb rule for or domain size? No, there is not thumb rule, but you can see that as I told while describing this problem, that you have to choose the domain such a way that boundary effect doesn't influence the solution, right? So now you have to choose the domain such a way, say like where you will put the inlet. Say if you put inlet here, maybe it will affect because it is very close to the cylinder. Maybe if you are outlet, if you are putting here, so maybe it will affect. So the solution. So you have to choose the domain such a way that it will not affect the solution of the problem, and you should not choose very bigger domain as well, because you have the restriction of using the number of grids, because if you increase the number of grids your computational time will increase, right? So that means say means if it is a three-dimensional problem, then obviously you can imagine that how many grid points you need to use. So obviously domain size is more, then your computational time will increase. So you have to optimize the domain such a way that its effect on the solution will not be there. And that for that, say 2-3 domains you choose based on your idea, and see that if there is no change after a certain increase in the domain, there is no change in the solution. Say maybe within, say let us say 2% or 3% there is a deviation, so you can go ahead with that. Or if it is a two-dimensional simulation, obviously if you can afford more grid domain and more grid, then you go up to 1% or less than 1%. Okay, so that way you have to do the domain independent test, and similarly you have to do grid independent test, not only domain, because now you have chosen the fix the domain. Now you increase the grid size. Is your solution changing with the increase in grid size? If yes, then that is not your grid you should choose. So you have to choose the grid such a way that after increasing the grid further, the solution doesn't change. Ideally, you have to actually, when you are doing the grid independence study, ideally you have to double the grid. Say if you are using, say let us say x number of grid first level, then 2x you use, then 4x is used, then check is there any change in the solution. So what solution you will check? Say maybe some parameter, like average drag you can see on the cylinder. Okay, if it is an unsteady flow, Struel number you can see, or if you are solving heat transfer problem, Nusselt number, average Nusselt number you check. Okay, or some other problems. So let us say you have this central region. Central region you plot the velocity profile, whether with increase in grid these are changing or not. If say this falls means up to a certain percentage, then you can have the minimum possible grid where further increasing the grid there will be no change in the solution. No change means you cannot ensure that zero, obviously within some limit. Okay, maybe 2% or 1% or 4%. How much accuracy you want, based on that you will fix that criteria. So this question I have already discussed. Okay, trigonometric equations. Okay, in the elliptic nature. Okay, so that you can go through my lecture and you can actually check it. Okay. Again, I don't want to discuss here. So like another question may be like this. Say when you are asking, let us say you have given that you have alpha. Sorry. Alpha del 2 pi by del x square plus 8 del 2 pi del x del y plus 2 del 2 pi by del y square is equal to 0. Okay, so this is the equation given. Now you are asked to find the value of alpha such a way that this governing this partial differential equation will become parabolic. Okay. Okay, so now you know how to mathematical characters of the equations, right? Parabolic, how we can do. So that will be just b square minus 4ac is equal to 0. Okay, b square minus 4ac. You have to, it has to be 0 for parabolic nature. So now say a is alpha, b is 8, c is 2. So you can find from here what is the value of alpha. So alpha, so now you put it here, so you will get alpha is equal to 8. Okay, similarly you have another equations, right? 1 minus Mach number square. So it is a steady compressible flow, d2 pi by dx square plus, sorry, del. It is a partial differential equation. Del 2 pi by del y square is equal to 0. Okay, so this is a steady compressible flow equation. Now you have to find the value of m, which is your Mach number, such a way that this becomes hyperbolic in nature. Okay, so now again you know the mathematical characteristics. So you know that for hyperbolic in nature, b square minus 4ac should be greater than 0. So from here you see that b is 0, a is 1 minus m infinity square, and c is equal to 1. So if you put it here, so you will get m infinity should be greater than equal to 1. Okay, so if the Mach number is greater than 1, then this PDE will become hyperbolic in nature. Okay, so this way you can practice some questions. Okay, from some books. The list of the books I have actually given in the module 1. Okay, some lists. So you can actually go through some books for better understanding. Okay, whatever we are defining, that is means in our course we have discussed, that is fine. But if you have any doubts or for further study and also solving some problems, you can refer some books. Okay, so another problem, let us say we solve. Let us say that fx is given. Okay. So fx is given as e to the power x. Okay. This is the function given. Now you use the delta x as 0.1. So this is the step size. And now you are asked to find df by dx, which is your f prime, okay, x at x equal to 1, okay, using forward difference formula. Okay. Now you can have the exact solution also here, because fx is known, e to the power x, and numerically also using forward difference you find the f prime x at x equal to 1. Now what is the percentage error you are asked to find? Okay, so you can see that exact differentiation you can have, okay, as e to the power x only, right? So now if you have, so it will be 2.718. Okay. Now numerically, if you want to find f prime x using forward difference, then obviously you will use f x plus delta x minus fx divided by delta x. Okay. So now f prime 1, you can find that f1, now delta x is 0.1, so it will be 1.1 minus f1 divided by 0.1. So if you find it, it will come as 2.859. So this is the numerical, means you can actually using the numerical differentiation, so you are using it. Okay. So now you can see that there is a difference. So numerically you found this with a step size 0.1 and exact is 2.7.18. So now you can find the error. Okay, so percentage error is 2.859 minus 2.718 divided by 2.718 into 100. Okay, so it will be around 5.2%. Okay, so you can see now if you change the delta x, so delta x, if you minimize, let us say 0.001 or yeah, so obviously you can see that this error will decrease. Okay, so this kind of some problem you can solve, okay, from some books. Okay. So if you have any other questions, so we'll discuss. Otherwise, we'll close the session. Suman, it is fine. So you can have any other questions you can post in the discussion forum as well. Okay, we have a discussion forum, right? So there you can post. We will reply, okay, to your queries.
Okay, sir.
Okay, then thank you very much. Anyone, Dr. Pallavi, you have any question?
Hello, sir.
Yeah, hello. Good afternoon. So can you please introduce yourself?
Yeah. I am from Maharashtra. I am chemical engineering graduate, and I completed PhD in chemical engineering from Institute of Chemical Technology.
Okay.
And now I want to revise my theoretical concept regarding CFD. I have hands-on experience in ANSYS Fluent.
Okay, you are working somewhere?
Right now, no.
Okay, so ANSYS Fluent, you know then?
Yeah. I did CFD simulation, 3D transient simulation during my PhD tenure.
Oh, very good. So then means obviously you have done before any CFD course means in your PhD or undergraduate?
Yeah, I completed one credit course which is required for a PhD.
Okay, then that means when you were using ANSYS Fluent, you are not using as a black box, right? You had
No,
means
no.
good knowledge about CFD. So that is the that is required actually. Say
Yes.
students who will be using some software. Software using is very good, right? So like COMSOL. Nowadays it is having very good multi-physics problem you can solve, right? If you want to write your own solver, obviously it will take more time and getting correct results is difficult. But with your good understanding of CFD, the problem, the governing equations, physics of the problem, if you use, then obviously you are better user, right, of the
Yes.
software. Otherwise, you will, maybe I have seen some undergraduate students without doing even CFD course, fluid mechanics course, they use this kind of software. So obviously, say if say it is not converging, or how to choose the grid, what quality you should have for better solution, right, and better convergence. So those things you will get when you come through this kind of courses. Okay.
Yes.
Good. Thank you. So again, we will meet. Suman, you want to say something? Yes.
Yes, sir. Sir, I have a question.
Yes.
Sir, I have typed in the chat box. Sir, in your lecture, sir, you have mentioned that the explicit method is easier to solve than the implicit method. Now, my question is then why do we use implicit method? We could have always opted for explicit method and solve the problems. Why do we go for implicit, sir? This is my question, sir.
Okay, so that you will understand later. Say explicit method when you use, so there is a restriction. There is a restriction in choosing the delta t, the time step. Okay, so there is a CFL criteria where you cannot go means above some delta t for your domain size delta x. Okay, so otherwise it will, so delta x will be very small. Okay, but if you are using implicit scheme, then most of the time these are unconditionally stable scheme. When you will learn stability, that time you will know, and you can go for higher delta t. Okay, so your solution time may decrease. Okay.
Okay.
But in terms of solving the problem, explicit is easier, writing the code and other thing. But implicit method, because you have to solve a set of equations, right, in implicitly. So that gives you some complexity while writing the solver.
Okay.
Hello.
Yes. Yes. Can you please introduce yourself, Mr. Kartikeya? Yes, you are audible.
Yes, sir. Sorry, sir. Actually, I was taking that lecture on your YouTube. So now I joined. Actually, currently I'm working as an assistant professor in a government engineering college, Nagaon, and I have done my MTech from IIT Patna. And last year in July semester, I did a course on fundamental of CFD by Dr. S. Vengadesan sir from IIT Madras. So in that course, actually, what provide a code, and on that on the handwritten code, and by that code they try to solve the problem. But the problem which I was facing at that time, like how I can draw geometry with the help of that code. And one thing I want to ask, like we have ANSYS software already present. So is it better like we can use that ANSYS software, or we should continue writing code and then trying to solve the problem?
Say it's depends on your interest, obviously. Say for a long term, if you plan, and if it doesn't involve a multi physics, then and for better learning for the students. Okay, it is better to start with writing a code. So they will know how to write, how to solve the set of partial differential equations. Okay, those things. But now if you are interested in something different, say that is the training to the students. Okay, in CFD, in coding. And the other perspective is that now you are interested to solve some industrial problem, let us say. So if you are interested to solve industrial problem, there is no point in writing the code, because writing the code and solving a three-dimensional, writing a three-dimensional solver with some physics, it will take itself maybe more than 1 year or so, means for a PhD student, okay, or some student. So obviously, if you are interested to solve some industrial problem, it is better to go using some commercial software, having some safety knowledge. Okay, most of the time that I was discussing earlier, that the undergraduate students, they don't have any background of CFD, but they use it and they have many questions, or they come up with some vague results which are not actually physically correct, right? So when you have some understanding of CFD, and if you use some commercial software to solve a problem, industrial problem or a multi-physics problem, then you can actually address the physics of the problem. Okay. Then you can use the commercial software. But say numerical way, if you want to address some problem, that you want to develop a better method or better scheme or some multi other physics, and for training the students, obviously you can go for writing a solver.
Okay. So I think solver is it is a basic of answers. If you know how to write the code, then you can understand the answers better. Okay, that is, I feel also like before doing that course, I do not know very much in answers. Like there are some things like simple algorithm they are using, and so many things are present. Also, after doing that course, it will become more clear. Like so, I think okay. Now I got your point. Okay, thank you, sir.
Thank you. So if you have any question, yes.
Sir, just a couple of questions for you, sir. First of all, sir, when we will have the next interactive session with you, sir, and sir, and the final thing is that, sir, I have heard from a friend. He said that nowadays, if we publish papers based on result got from ANSYS Fluent, it gets rejected.
No.
They prefer open form. Is it true?
No, that is not true. So, okay, first let me ask the first question. Okay, so we'll have total 3 interactive sessions like this. So one is over, another 2 will have. Okay, and maybe in the middle of the maybe in the next month we'll have, and I think my other 2 TAs are having interactive sessions regularly, right?
Okay, I haven't followed it, sir. I haven't followed it, sir.
Okay, so 2 PMRF, Prime Minister Research Fellowship students are actually conducting live sessions every week. Are you attending it?
Okay, sir. Sir, I haven't attended yet, but I will do it in future, sir.
So they are very good students, okay, having good background of CFD, and they are with regular contact with me. Okay, those two students are from IIT Madras. Okay, so they are actually every week they are having these live sessions. Okay, you can if you have any questions there also you can, and they are discussing different kinds of so let us say today I have solved few problems, maybe they are solving few problems. Okay. Second question. So now now earlier there was some hesitant, but in the publishing this agency, but now say ANSYS Fluent, COMSOL, then OpenFOAM, or let us say Basilisk, especially for the multi-phase flow problem. These are now well accepted by journal community, but you have to address the physics of the problem correctly. Say, only solving the problem, getting some results without much correctness or physics of the problem, without discussing physics of the problem. Say someone is writing paper, then obviously it is having lower value. But if you are using as a tool and addressing the problem properly, physics properly. Okay, and obviously, as I told that about the correctness of the solution. If it is okay, then there is no problem. Say our group, our PhD students publish this paper using Comsol or some commercial software, Basilisk, like that. Okay.
Okay, sir. Okay, sir. Thank you, sir. Thank you very much.
Okay, thank you. If you have any other question, you please put up in the discussion forum, and you please attend live sessions organized by this PMRF fellows, because these are these will be very useful for solving some problems. Means preparing for these your tutorial. Tutorial as well as say exam problem. Okay. Thank you for attending, and it was having nice interaction with you. All of now 3 are there, and so it was a very So if you have any doubts, and you please put it in the discussion forum, and if you have some personal you can contact me through my mail. Okay.
Okay. Thank you, sir.
Okay. Thank you very much. Bye bye.